Okay, let's start today's lecture. So we are going to look at vision language models today. It's a very hot research topic. But let's briefly remember what we have seen last week. We have looked at self-supervised learning in two main categories. The first one was predictive modeling. The second one was agreement-based learning. In predictive modeling, it's basically we have an input which is unlabeled, but we mask some part of it and try to predict that masked part. This is basically predictive modeling. Or you have an input, you apply some transformation to it, like rotation, and try to predict what was the modification, how many degrees was it turned, and so on. In language, this is heavily used as next token prediction or masked word prediction, or also with early SSL methods in vision, we use predictive modeling. In the second category, it's a slightly different. We have representations from different views of the input, and they should agree, while representations from different inputs should be dissimilar, and there were several different subtypes of this category: contrastive, non-contrastive, clustering-based, and distillation-based. Next token prediction, your training objective is something like this. You're trying to maximize the probability of token xt given all the tokens up to t from the start of the sequence. In masked language modeling, the objective is bidirectional, not causal as in here. We call this a causal objective because you only look at the previous elements. Here you look at all elements except the one that you masked. You're trying to maximize the probability of xt with given everything in that sequence except xt. So this is predictive modeling. Another type of predictive modeling was next sentence discrimination, which specifically the BERT models used. You have a large corpus from Wikipedia, let's say. You give two sentences that follow each other, and your model should say, yes, these two sentences follow each other because the second sentence follows the first sentence because their flow makes sense. But if you take randomly two sentences from far apart places, then the flow will not make sense and your model should say no. Similar ideas of masked language modeling was also tried in vision. We looked at two models, SigMIM and MAE, masked autoencoder. You basically mask randomly some of the patches and then you force your transformer to predict those masked parts, and both of these use pixel-wise losses. And then we looked at agreement-based modeling. Here I will try to remind you the most important tool, which is SimCLR, which really started this type of agreement-based modeling. And the best we have today, which is Dino. So SimCLR and Dino, let's remember those. SimCLR, you start with an image which is unlabeled, and you take two augmented views of it, and these augmentations are drawn randomly from a predefined set. So from the same image, you get a view 1 and view 2. You pass these two images from your neural network, and then at the end, you get some representation. Representation, you can also call Z as representation. You try to maximize the agreement between Zi and Zj because they are coming from the same image. But let's say there is another image in the same batch. You apply the same things to it, same processes, but again, random augmentations. Now, the Z vectors computed from these different views should disagree with Zi and Zj. This is the idea of SimCLR. So in a sense, it is treating each image as a class in itself. You take two images randomly and you assume that these are two different classes and their augmented views should disagree, but augmented views within each image should agree. That's why we also call these methods as instance discrimination methods. I'm not sure if I said this last week. Instance discrimination method. And then after SimCLR, we had Moco, Buyol, and so on. There are many SSL methods, but all of those convert to Dino, which is the best self-supervised learning algorithm in vision today. We have Dino V3, but the crux of the main idea is here. The other things are really mostly large data, pipeline improvements, maybe a few new losses, but the main idea is here. Again, we take an image and we take two augmented views. These are fed to a student network and a teacher network, and these are the same architectures. So their parameters, architectures are the same, but of course their parameters are different. Student network is learned using backpropagation by minimizing the loss, but teacher is updated continuously by the recent weights of the student. So this EMA is exponential moving average. It's a moving average of the student's parameters. That's what we call teacher. And what is happening overall in a high level is that the teacher is producing labels. P2 you can think of P2 as labels, and which is output by the softmax. So this is like a probability distribution. And student also outputs a probability distribution P1. At the end, you try to minimize cross entropy between P1 and P2. This is what Dino is. To prevent collapse, they do things like centering and sharpening. But those are details right now, but they are important. Okay, so that was the overview of last week. If you have any questions, we can discuss. Yes. Yes. So X1 and X2 are two augmented views, two differently augmented views of the same image. And augmentations are sampled randomly. So you are essentially forcing you can think of these as labels because it's output by softmax. It's a probability distribution, but it's not a one-hot vector, of course. It's not a label in the ground truth sense, but it is still a probability distribution. So you can think of this as label and this as prediction, and you do cross entropy.
Representation. How is it used to collect different classifications?
Yeah. So you discard everything except the student, and you use student you take it, and then you either you put a linear layer on top, freeze it, and then use it for your task, or you can still fine tune it.
So we only use the ratios.
Yes. Yeah, the result of Dino is this. The target is to get the weights of the student. Okay, so let's look at today's topics, vision language models or vision language modeling. We'll start with an intro, and I will try to discuss open vocabulary, zero-shot recognition, because it's conceptually very different from what we have seen so far. We have looked at closed set recognition in image classification. Next, we will talk about image caption datasets because these are actually the crucial things to train VLMs. Image caption datasets are probably the central, most important piece in this whole thing because the main value is in the datasets actually. CLIP, the most famous VLM, contrastive language image pre-training model. And then after that, we look at SigLIP. These date back to 2021, 22. There are many other VLMs, but I'm going to talk about SAIL, which is CVPR this year. So it's a very recent vision language model. It's a good showcase of where VLM research has come to. We will briefly talk about other VLMs, and then I will close with a very nice paper, which is NeurIPS 2024. It's also very recent, which says that, so up to this part, so up to here, we will talk about all the positive things about VLMs, right? They do great things. They are super powerful, great. But the last paper will say that it's just supervised learning and they don't generalize well. There is no magic. Okay. And actually, on the contrary, it looks very pessimistic. Its scaling trends look very pessimistic. So it won't scale. It's not the way to go, the main message of that paper. So, okay, an administrative note. I hope you started doing homework too. It's due on December 9th. It's not a difficult homework. The main thing is to implement those different positional embedding methods and of course VIT. I think it's a very educative homework, so not difficult. But let me know if you have any questions, if there are any unclear points. Recommended reading for this week is the CLIP paper, Learning Transferable Visual Models from Natural Language Supervision, was published in ICML 2021. Very highly cited paper. I think you should all read it if you have not read it yet. Okay, let's start with the open vocabulary zero-shot recognition. Suppose that I have a robotic task. I'm trying to make a robot, and that robot is going to deal with objects like this. Okay, these are some cubes, cylinder, sphere, those kind of objects. And to deal with these objects, you have to, of course, recognize these objects, whether it's a cube, whether it's a sphere, whether it's a cylinder, because that recognition will give you a plan of how to manipulate that object, how to grasp it, or I don't know. So you have to recognize these objects. And what would be the classical way of doing this, solving this task? The classical way would be you collect lots of examples for each class, right? So you crop the cube, you crop examples of cube, many of them, label them as cube, and then put it in the data set. Next class, you crop images of spheres, different colors, different sizes, different viewpoints. The higher the variety, the better. You collect these, put it in your data set, and then you do it for the cylinder as well. Now you have a 3-class data set. This is the classical approach that we have did so far. You have a 3-class data set, image classification data set. You train your favorite CNN or VIT on this data set, and now you have a classifier. Then you can, your robot can now decide whether which object is a cylinder, cube, and sphere, etc. This is the closed set recognition, the classical approach. But after VLMs are out, now we have the VLMs, we can do another approach, which is open vocabulary and zero shot. Open vocabulary means you are not restricted to the set of classes that you decide. So we said there are 3 classes, sphere, cube, cylinder, but this is called closed set. But in open vocabulary, you are not restricted to these 3 classes. You can say shiny object. You can say objects with corners. You can say red object. Or you can combine these things. So the vocabulary is now open. And zero shot means you don't have to train anything. You will not train any model. And it will just still work. So VLMs give us that capability. Classical approach is to train task-specific training. But VLMs can do zero shot. You don't need to train on the task. Classical approach uses closed set labels. Your labels are set, you decide them, you fix them. Adding another label later, you can do it, but it's costly, right? You need to bring images for the new label, add it to the data set, and you retrain your model or fine-tune it. So it's a costly thing. Versus in VLMs, it's open vocabulary. You can decide on the fly, I want to use this class name also, and you just use it. So as I said, classical approach uses closed labels. We collect data, label them, and train the model. But the modern approach, which uses VLMs, we start with a pre-trained VLM. We download this VLM from the web. It's usually on Hugging Face or somewhere. You take it off the shelf. You decide on your vocabulary that you want to use, and then just use it. You give your vocabulary to your class names to the VLM, and then your VLM can do, without any training on this specific task, will give you some good accuracy. If that accuracy is not good enough for your task, for your requirements, you can, of course, further train, fine-tune this VLM, or just the vision encoder part of it, or the whole of it. But usually, VLMs are trained on massive data sets. They, out of the box, know lots of classes. So it is possible that it would just solve your classification task without any training. So to demonstrate this, I did a small experiment. I downloaded a SigLIP model from Hugging Face. SigLIP was proposed in 2023, was published in ICCV. And I opened the Google Colab notebook. I ran it on the cropped objects from this image. Okay, I cropped some objects, actually all of them, and asked them to SigLIP without any training. So I first tried these 3 classes. I asked it to classify it into either cube, cylinder, or sphere. And as you can see, these are the class probabilities that SigLIP gave me, which is correct. I tried other objects, cube, cylinder, as you can see, is again correct, and sphere is again correct. I did not do any training at all to do this. Next, on the same images, I tried other labels. For example, glossy object, matte object. And it does a good job there as well. This is not very shiny. It's not glossy. So that's why SigLIP gives higher probability for the math class, but for this one, it's more glossy than math. I asked it to classify the object into round or object with corners. Again, correct. And then I even tried counting things. So I give this one and I put the labels as one object, two objects, or three objects. And it was able to count the objects in the image. So here one object has the highest probability, here two objects, here three objects. So how this is possible? How is this possible? We are going to learn today, okay? Are you impressed with the capabilities of VLMs? We didn't. No, you are not. Why? Okay. But it can see. Yes. Anybody who is not impressed? This is very impressive. Yeah, as someone who did research in this many number of years, this is super impressive. Because for each of these tasks, usually you collect a data set, you train a specific model, right? It's too much work. It's very costly, but this thing is just, you can imagine any label. You can combine two glossy objects and one matte object, things like those, and it will just work. The classical approach, you have to train things and it's still closed set. It's very restrictive. So how does this work? Oh, before that, there's this slide is from SigLIP's author's talk at ICML 224, Lucas Beyer. It's basically the same concept that I tried to show you with some more fancy images. For example, so this image, a cow in a suit, look at that. A cow in a tuxedo, a cow on the beach. So both captions are correct. But for this cow, only the cow on the beach label has high probability. As you can see here, a cow in a tuxedo is 0% for that, which is correct. So this is very impressive. You can imagine any kind of label here. That's why we call it open vocabulary. And then it will give you, of course, it will make errors. It's not perfect, definitely. But it's much better than what we have in the classical vision sense. Okay. You can make the labels also very, very long. Look at this. A picture of a laptop with lock screen on. Window reveals Lake Zurich and the Alps, blah, blah, blah. And see, look at this. It's actually a very good description of the scene. Okay. So, how is this possible? This is possible mainly because of supervision, because of data. But how is it possible to label these things, right? So if I give you images like this on top, coming up with all of these labels and all possible combinations, imagining all possible labels and doing the annotation is a very costly thing, right? It's not scalable, it's not possible. But fortunately, we have image caption data sets which are collected from the web. So these are internet scale data. And with this data sets make VLMs possible. Now let's look at the data sets. Historically, this is one of the earliest ones, MS COCO captions. MS stands for Microsoft, COCO is for Common Objects in Context. And this data set was it is still the most widely used benchmark in object detection. So it's still being widely used. So it's originally an object detection data set, but researchers have provided captions for them. So for each image in the data set, they provided captions like this. So you just plain English description of the content of the image. A large bus sitting next to a very tall building, a bunk bed with a narrow shelf sitting underneath it, and so on. A horse carrying a large load of hay and two people sitting on it. So, of course, these descriptions are not perfect, and they provide 5 captions per image, and these 5 captions are different because different people annotated. For example, for this image, another annotator might say there is grass background, grass field in the background, there is a road or something like that. Some people describe it more, some people describe it less. So you have a variety in captions. There are 300,000 images, 5 captions each. And the data set, this data set is widely used today for evaluating captioning models, text to image and image to text retrieval models. So this task, captioning task, is you are given an image, your model has to produce the caption. This is called captioning. These two are retrieval tasks. That means text to image is you are given a text. For example, you are given this caption as the query. Now, from within this large data set, you have to retrieve the correct image that matches this caption. This is called text to image retrieval. And you can have the other way around, image to text. So I give you an image as query, for example, this one. Among all the captions in the data set, you have to bring the correct caption. This is like closed set classification, but it's retrieval. You rank things in the data set, but it's not open-ended. It's not open set. It's still within the data set. Later, there was this data set, conceptual captions, CC3M. This is an order of magnitude larger than MS COCO. You know that an order of magnitude means 10 times, right? So 10 times larger than MS COCO, 3 million. And this is web scraped from, if you know HTML code, to put an image, you use the image tag. And within the image tag, there's an attribute called alt, this one. It's optional, it's not mandatory. You generally put the description of the image in the alt attribute. And this was originally intended for non-graphical web browsers. Have you used one? Links, for example, it was called Links. Non-graphical, it only shows you text in a terminal. There is no graphics. Anyway, so there were non-graphical web browsers, and for those, if there's an image in the web page, since it cannot show the image, it will show you the alt description of the image. So that was the purpose of this. And then this is the data set widely used for training VLMs. It is still being used, but now there's a better data set called Lion. We will talk about it. But yeah, this is still being used. And here are some examples. Image and alt text, image and alt text, and then conceptual captions. These, in this paper, they do some filtering and modification to the captions. I think I believe I have them, but we can talk about it. But the main idea here is you collect such data from internet. There is something called command crawl. Maybe you heard about it. This is a repository of all the web starting from 2008. So since 2008, command crawl is continuously crawling the web and then saving all the web content in this I wouldn't call it a data set because it's not created in any way. It's just a storage of all the pages in the internet. So common crawl. So you go to common crawl, it gives you all the pages and you look for image tags. You download the image tag from the URL and then associate the alt caption with that image, and that you get a data set. You get an image caption data set. CC3M, since the web is noisy, so it's not a good quality data set because alt texts are sometimes simply incorrect, sometimes empty, sometimes correct, but it's not a full sentence. It's just a list of words and so on. And not all images are good quality. So to deal with that, CC3M designed a 4-step filtering method. First, they filter images based on size, aspect ratio, encoding format, and offensive content. So if, for example, the aspect ratio is too extreme, you have like a horizontal image very long or a vertical image, you just discard it. They discard anything but JPEG and so on. The details are not really important. They do text-based filtering based on language, capitalization, token frequency, predefined unwanted phrases, and so on, sentiment, polarity, adult content. So there is really a major effort went into filtering. Third, they do image text-based filtering based on number of image tags that overlap with existing text. So here they look at the image content by using a model, Google Cloud Vision API, and that Google Cloud Vision API tells you what is inside the image, and they measure the similarity of this with the caption or the alt text, and then use this as a criteria for filtering. And text transformations, they, for example, replace these names with actor. So they remove the person names and replace them with their profession or role, and so on. So this is what they did. CC12M, which is later in CVPR 2021, relaxed these criteria because they argued that CC3M filtering was too restrictive. When they, for example, look at this jellyfish image, and this is the alt text of that jellyfish image. And CC3M filtering rules discard this image text pair. But CC12M keeps it because they argue that this, although it doesn't look like a proper caption, it still has great information about the content of the image. And it is, I think, true. You see some hashtag jellyfish, blue ocean. So it is descriptive, but it's not a proper sentence, but still it's, so this is part of CC12M, but not part of 3M. So 12 million, 3 million. Hand holding a fresh mangosteen. I don't know what mangosteen is. Here, person, Trump, was the first US president to attend a tournament in Small Salot Arena. And so I don't know why CC3M eliminated this, but so dataset creation is a major effort. It's not trivial, it's not easy. Yes. They are English only, yes. And it's a restriction. But now we have multilingual caption datasets today, not CC3M. They also, in their paper, proposed a captioning model, which I'm not going to go into detail. It's a CNN takes the image, produces image embeddings, and this is fed to an encoder, RNN. These are RNNs. RNN outputs some summary of the image, and then a decoder RNN takes this image summary and produces the caption word by word in an autoregressive manner. So this was the state of the art in 2018.
And from that, as like images, things which we take images.
Text with?
Text that are in the images.
Oh, okay. There is text within the image.
Is that data?
That's a very good question. Normally, to detect text in the images, it's called the OCR task, optical character recognition. But these VLMs are not OCR models. But I think, yes. Yeah.
So they work.
Yes, I think they are pretty good. I know it from our own research. When there is text in the image, so when you do a nearest neighbor search, for example, it will group together images that have the same text on them. So I think it has a reading capability, but not as good as OCR, but yes, it reads text. Yeah. And then, yes, this is CC12M. We can now take a break, 10 minutes, and then continue with the Lion. Okay, we looked at MS COCO and then CC3M datasets. Now let's move on to the Lion dataset family, which is the most influential dataset for VLMs today. This is a family of datasets because there are many different versions. It's a massive, non-curated, openly available image text pair dataset created by the non-profit organization Lion. There are several variants, Lion 400 million and 5 billion. Look at the numbers, these are massive scales. It's again built from common crawl, which I talked about in the last hour. So captions are taken from the alt text or surrounding text in web pages. They filter image text pairs using clip similarity scores to increase semantic alignment. NSFW not safe for work and watermark filters are also applied. Still, it's very noisy. That means there are duplicates, so deduplication is required. Additional cleaning is required for high quality training. And this is a major effort. Widely used for training VLMs and diffusion models today. So not only VLMs, diffusion models, stable diffusion also use this dataset. And it's the foundation for open multimodal research. Multimodal here referring to the two modalities, vision and language. Includes copyrighted and sensitive content because it mirrors the public web. That's why there are ethical and legal considerations, and these are still ongoing. Not only image caption dataset, but Lion, for example, also, this is very recent, November 2024, they announced a collection of 12 million links to publicly available YouTube samples paired with metadata to support machine learning research in foundation models for generic audio, music information retrieval, audio datasets, and so on. And there's a new version of the Lion 5 billion. It's called Lion 5 billion. It's a transparent iteration on the Lion 5 billion. So this just shows that there are some legal and ethical concerns. That's why they try to iterate this and create newer versions. And basically, these datasets are nothing but text They release URL, caption, and that's it. So they don't give you the data set. They give you the indexes. And by using that indexes, you download the data set in your local machine. Okay? Because they don't have the right to distribute all these images on the web. They just provide links and the captions. There are many other data sets. It's difficult to cover all of them and not necessary to cover all of them. But as you have seen, creating a quality data set from the web is a major effort. It's not trivial. And there are even entire papers on this. Okay. I don't know why my link is not working, but I just want to show you this MetaClip repo on GitHub. It's impressive. So they published a series of papers out of this, from NeurIPS to ICLR to CVPR to EMNLP. And what they do is actually, this is like a pipeline of how to create and extract a data set from the web. And related to your question, this is now not only in English, but also multiple languages worldwide. You can do worldwide training. So it's a major effort. So the people have written many papers, entire papers on how to create these data sets from the raw web data. And importantly, some companies have their own closed data sets. For example, CLIP, OpenAI, has a 400 million image caption data set, which they don't disclose. It's closed. And it's probably a very high quality data set, and they probably spend lots of time and money on it, and they don't share it. And that gives you the quality of their models, actually. But people are trying to replicate that high quality data sets outside of OpenAI, of course, and MetaClip is such an effort. Okay. Once you have an image caption data set, for example, Lion 400 million or 5 billion, what can you do with an image caption data set? There are several things that you can do. First, you can take an image as input and give it to your model, and you can force your model to generate the caption. Okay, so this is called captioning. And an example for this is the contrastive captioners. We will talk about this briefly in the later slides. So image in, caption out. You can do such a training using an image caption data set. Second, you can give caption to your model, and then it could produce image. Now this is generative image modeling. An example would be DAL-E, stable diffusion. Yeah, there are lots of. But the important point here is that you use these image caption data sets not only for VLM training, but also for generative training of generative models. And third, you can give your image and caption to your model. It can create embedding image, embedding caption, and then it can also give you a similarity score. And this is the typical task for when we say VLM. vision language modeling, we typically refer to the third task. But all of these tasks are actually vision language modeling because you are trying to model vision data and language data at the same time. So all of these three are vision language modeling, and all of these three are multimodal data modeling. Because image is one modality, language is another modality. But when we say VLM, we refer to the third one. This is the CLIP style, CLIP and SigLIP style VLM modeling, and this is what we are going to talk about in the remaining slides. Okay, so let's talk about CLIP, contrastive language image pre-training. CLIP is actually, CLIP is a super impressive model, super impactful. It changed everything, I think, in, well, lots of things in computer vision and machine learning. And it's so simple to explain. This picture actually explains the whole training, its whole training idea, and also the inference idea. So let's talk about this training, how they do the training. You start with a batch of image caption pairs. Here you have a batch of images, batch of captions. Of course, they are coming from your dataset, Lion, for example, or CC3M, CC12M. And each image has its ground truth caption. You pass the images through the image encoder, and it calculates or computes these image embeddings. Let's call them image embeddings. For example, ResNet 50 based CLIP produces 512 dimensional vectors per image. So you give it an image and it outputs 512 numbers. So each I1, I2, I3 is such a vector. In parallel, you feed the captions to the text encoder, and now these are text or caption embeddings. It's better to write caption embeddings. Okay. Now, the task is to, you have a batch of n image caption pairs. The task is to compare the image embedding of the first image with all the caption embeddings within the batch. And the correct match is image 1, text 1, image 2, text 2, image n, text n. What we want to do is to maximize the alignment or similarity between I1, T1, I2, T2, and minimize the similarity between image 1's embedding and the captions for all other images in the batch. Okay, very simple idea. And actually, we have seen this idea in self-supervised learning, and we called it, what did we call it? Attention, not exactly. It's a loss. Triplet loss. Close, yes, it's very similar, but we didn't use triplet loss in self-supervised learning. We called it something else. We are comparing things. Contrastive. This is contrastive loss. Why? Because you are contrasting image embedding of the first image with captions of all other images, right? And you are trying to maximize the correct match, minimize the incorrect matches. Contrastive loss. We actually used specifically the information noise contrastive estimation loss. Here in the paper, they show a pseudocode, which is very easy to understand. It basically does what we described. I'd like to show you the loss functions because that's the important part. This is the info and C loss that we talked about, contrastive loss. Okay, let's look at the loss on top right. Here, X represents the normalized embedding of images, as you can see. F is the image encoder. Okay, so I took this loss equations from SigLIP paper. Therefore, it's not in full agreement with the picture because the picture is taken from CLIP paper. But yeah, sorry for the confusion. But XI is the embedding of the ith image in the batch, and YI is the embedding of the ith caption in the batch. And these are normalized, okay, L2 normalized. In the loss, you see that we have dot products between image embedding and text embedding, and we have a softmax. You should be able to recognize this structure from previous lectures. So we have image and text embedding dot products for all possible pairs, and then you apply softmax on top of them. And we try to maximize this xi dot yi value because it's the dot product of the embedding of image I and the caption of image I. If you write it like this, the softmax will just try to increase this value because we are minimizing this loss and because there is minus here, right? We will try to maximize this similarity and minimize the other similarities where I is not equal to J. They write two components of the loss. One of them, image is like the central piece or like the query. So I here is the anchor. So you have a loop over the batch or each image caption pair in the batch, but in the first term we compare xi to yj's, but in the second term we compare yi to xj's. That's it actually. Does this loss make sense? Can you understand it? It's just looks like cross entropy, but the distinction is that we are using similarities within the exponential function, and similarity is measured by the dot product of two vectors, two embedding vectors. As a technical contribution in this paper, they propose a learnable temperature parameter. So this T you see there, T, it scales the dot product, and they made T a learnable parameter and just let the network learn it. And they showed that as training progresses, this T increases, and then it makes the predictions sharper. Usually in temperature softmax, you treat T as a hyperparameter and try lots of different values and try to find the optimal value. But here in this paper, they tried to set it in a learnable manner, and it worked for them. Now that we trained our CLIP model, how do we use it for inference during test time? And this is the open vocabulary zero-shot let's say open vocabulary only. Open vocabulary method that we talked about in the beginning. I can create a set of classes however I like. Let these be class names. I create captions out of them using templates. And one template could be a photo of a object. So you put your class name here. There are many different templates. They actually used 80 different templates in the original CLIP paper. For example, a high resolution photo of something, a picture of something, and so on. So you get different templates here. They all pass through the text encoder, and each different class candidate has now an embedding. What you do is take the embedding of the image, input image, and do dot product and return the one which has the highest dot product. That's the result, a photo of a dog. This is how CLIP works.
What is the dataset? And it is similar captions.
So this is a batch.
Similar captions.
Not even similar. They are ground truth. So image one. What do you?
The batch itself has, for example, two dots and very similar captions.
Okay. What will happen if you have two dogs with very similar captions? Yes, I mean, it will, I think, harm the training because the caption of the second dog will probably apply to the first dog, but yeah, it will be harmful for training. But we are talking about 5 billion image caption pairs. Probability of that happening is that it's small. So that's why it's noisy training. Yeah.
Instructions rectify the uploads of full uploads for the images or the automation will
Last hour I talked about this at the entire lecture. Captions. Okay, they use the Lion dataset. Or they use the closed source, closed dataset that they have, but it also was extracted from the web. So it's coming from alt attribute text. Okay, but we don't know what kind of curation OpenAI people did. They maybe sit down and write captions, probably, to make them high quality. Data annotation is a very significant business in AI. You know that, right? It's really a very large portion of AI business. Yeah, data annotation, labeling is, they probably use such services. They really put lots of money in it. So that's it. This is CLIP, nothing else. This was trained on 400 million image text pairs, closed data set. We still don't have access to it. Inference or training? Okay.
So in the training, the CENG501 is for different captions, right? But in the inference, we only put a single caption in with a max. And the singles as of exceptions, like why is the inference multiple?
So in training, you understand this, right? There is a batch. In the batch, you have image caption pairs, and this T and IN represent those. But in inference, this N, well, it's a bad choice because this N has nothing to do with the N in the previous picture. Here it's, yeah, let's make it clear. So this N is batch size. Okay, but here, this N is the number of candidate classes or captions. And this is up to you. If you want to do a classification using, I don't know, 10 different classes, the n is 10 here. Remember the example at the beginning? I used this model to classify sphere, cube, cylinder. In that case, n is 3. Is it clear now? Those n represent different things. So trained on 400 million image text pair, the largest ResNet model took, be careful, 18 days to train on 592 V100 GPUs. We don't have this GPU resource even as a nation today. I think Truba is a really good resource. It's not bad in any way, but about 100 maybe. Maybe some of you are using V100's Truba. There's a recent edition with H200s or something like that. So we have really good cards in Truba, but this is insane. The largest vision transformer took 12 days on 256 V100 GPUs. But fortunately, now we have VLM training methods that take much less resources. I will talk about it at the very end. But this was the first VLM model, clip-style VLM model, so it took serious resources.
How about that? Before the lectures, we talked a little about they tried to fix their model into two GPUs, and it was an architectural work behind. So I'm talking about the recent things. Are they still trying to do something like that? For example, for this one, I tried to fit the model into, for example, 500 GPUs, or the architecture is like that. There's like the processor master slave. It's already distributes the GPUs, the total work.
I'm not exactly an expert in that. It's really a different expertise now. But I don't see many examples of splitting a model into different GPUs. I don't see that. Instead, you use, if you want to use a large model and a large batch size, those things do not fit into your GPU memory. What you do is distributed training. So there are lots of GPUs, each processing a different image, let's say, a different image caption pair. And you collect gradients into one place and do the update like that. So yeah, I don't know of any examples which split the model into different GPUs, but instead you distribute the batch and collect gradients and do the update. But it's a serious topic. It's not something that you just do. It's a research area. So yeah, it took serious amount of resources, and the results were striking. On how many data sets? 27 data sets across 27 data sets. Zero-shot clip classifier outperformed a fully supervised linear classifier on top of ResNet 50 features on 16 out of 27 data sets. This was a striking result in 2021. So out of the box, zero-shot prediction on these 27 data sets produced very good results. But of course, you can discuss this, right? Because you can question this. Is this really zero-shot? Because in CLIP's massive pre-training data, 400 million image caption pairs, it probably have seen all of these data sets. But it's still a success to not forget each of these data sets, right? Still, it's doing producing good accuracy. Not only zero shot, but they also took their trained model, pre-trained model, and they did linear probe. We learned linear probe last week. Do you remember? You take a pre-trained model, freeze it, create a linear layer on top of it, and then only train this linear classifier in a classification dataset. This is called linear probing. So they take train clip, and train the linear layer on top of it. This is called linear probe. And as you can see, linear probe also using clip also produces the best results compared to, I don't know, VIT trained on ImageNet 21K, Instagram pre-trained models, SimCLR, Buol, Moco. These are the self-supervised learning methods that we have seen last week. So it's better than all of these things. But remember, these did not use any labels. These worked only on images without labels, but CLIP used a massive image caption dataset, so massive labeled dataset. Also, on distribution shift, the results are striking. What does distribution shift mean? Think of a class here, banana. The first row are images of this object in everyday life, some regular pictures, photographs. But there is ImageNet V2, version 2, where the objects have different appearances, and these appearances are mostly rare, not very common, okay? That's why this is called, for example, this is like a peeled and a zoomed in version of a banana. These are very green and not very ripe. So this is called a distribution shift. It's the distribution of the data set is different than the training data set. A classical example of distribution shift is in autonomous driving. You collect data in broad daylight in city X, a specific city, and then when you run your model on a different city under different weather conditions, that's a distribution shift, okay? And models usually don't generalize, they just fail. So distribution shift is a real test. If your models really can do well on distribution shift, then it means that it learned something. For example, illustrations, cartoons is also a distribution shift, right? Sketches, black and white sketches, it's also a distribution shift. Here, there is a stylized ImageNet. It's, or I don't know, these are weird, image object net. I don't know what these are, but these are difficult images to recognize. And there is ImageNet A. It consists of natural adversarial examples for the objects. For example, this is still a banana, but it's sliced on top of a plate, and models just look at this 2.7%. So you train a ResNet 101 on ImageNet, and it achieves 76% accuracy on ImageNet, which is good. But this model does worse on ImageNet V2, 64%. On ImageNet renditions, these are the illustrations, cartoons, 37%. ImageNet sketch, 25%. So basically means that it doesn't recognize these things. And ImageNet A, 2.7. But CLIP is strong in all of these things. So very striking result. But again, you can question this, because it probably has seen such images in its 400 million pre-training data set. So this is not like a true generalization, but it's supervised learning. Distribution shift is quantitatively measured by this plot. On the x-axis, you see average on-class subsampled ImageNet. So ImageNet accuracy top 1. And this average accuracy on the 7 natural distribution shift datasets. Usually what you expect is if your model is achieving a certain accuracy on ImageNet, for example, 80%, you would expect to achieve the same or similar accuracy on distribution shifted datasets too. But it doesn't happen. Standard ImageNet training is the blue curve. As you can see, it's much under the ideal curve, but CLIP is closer to the ideal curve. It's still under the ideal expected outcome, but it's closer than the classical supervised training. Okay. Now we can jump on to SigLIP. If you have any questions about CLIP, I can answer. So SigLIP is actually doing a very simple thing on top of CLIP. It replaces the contrastive info and C loss of CLIP with multiple independent sigmoid losses. So replacing contrastive info and C with binary classification losses. And this makes things much easier to train. So because it's not using the contrastive loss, it does not require a global view of the pairwise similarities in the batch for normalization. Because remember, in info and CE, you had xi, yi. In the denominator, you had e to the power xi, yj, right? This is the info and CE loss. And to compute this info and C loss, you need to access the whole batch. And you need to compare all possible pairs. It's an n-square comparison. But sigmoid loss only looks at this xi, yi. I will show you in the next slide. This allows scaling up the batch size, also performing better at smaller batch sizes. Here, let's compare the loss of CLIP and SigLIP. On top, you see the CLIP loss we have seen in a couple of slides back. And at the bottom, you see SigLIP. It's obvious that SigLIP's loss is much simpler. You only have xi, yj within the sigmoid. And there is this auxiliary variable zij, which is actually serving as kind of a label. So Zij is the label for a given image text input, which equals 1 if they are paired and -1 otherwise. So remember the sigmoid function. This is sigmoid, right? And remember its shape. So this is 1, this is 0.5, this is sigmoid. So for the correct match, correctly matching xi, yj, zij is 1. So we are actually, so it's e to the power minus xi, yj. That's right. For the correct pair, we are actually looking at e to the power xi, yi. I simplified it to illustrate the point because there is a temperature parameter T, there's a bias B, but you can drop them. The conceptual important part is here. Image I embedding, caption I embedding, this is the correct match. You want this to be high, right? You want xi, yi to be large. And for this large means you are on the x-axis to the right, positive values. And this becomes 1. Sigmoid is maximized here. Because of the minus, we want to maximize the sigmoid value. And that corresponds to maximizing the dot product, xi, yi. Similarly, you're trying to minimize the dot product between unmatching image and captions. So such a great simplification. SigLIP is simplified things, which is very nice. And look at the pseudocode of SigLIP. It's just a few lines. L2 normalize, embedding of the image, embedding of the text, take the dot product here, scale with temperature, add a bias, and then create this label matrix, which is 2in minus 1. So the label will be, so I produced an identity matrix, right? So it will be like this. You have plus ones in the diagonal and minus 1 in the off diagonals. And then you just do the sigmoid loss using this matrix. That's it. So simplified, very nice. And it shows superior results compared to CLIP on almost all data sets. Let's look at ImageNet 1K. This is with respect to different VIT sizes in the base size. The best results are shown with bold. As you can see, SigLIP is outperforming other VLMs, including CLIP, OpenClip, EvaClip, CLIP-A, and so on. Yeah. Today, I think there is SigLIP 2, an improved version of this, and they are performing really well. Any questions about SigLIP? Yes.
What about the training time of SigLIP?
Good question. I did not include it here. Well, I don't know on top of my head. Let's see. This sigmoid loss allowed to scale up the batch size. And because of that, maybe it reduced the total training time, but I didn't include it here. SigLIP 2 is SigLIP plus captioning-based pre-training, self-supervised losses like distillation, mask prediction, plus online data creation. SigLIP 2 models outperform their SigLIP counterparts at all model scales. The new training recipe leads to improvements on localization and dense prediction tasks. But the details are, if you are curious, you have to go to the paper. This is 2025, very recent. Mm-hmm.
What is this view?
Which one?
So, VIT size. What does it exactly mean?
This VIT size. It's the number of parameters in the VIT. B for base, L is for large. H is for huge. I don't know, GESO. So, largest one is E, enormous. G is gigantic. H is, what is H? I don't know. But in the original VIT paper, they had base, large, huge, I think. But people come up with names. If you create a 12 billion parameter VIT, you should call it, I don't know what. Okay, the last vision VLM that we are going to look at today is SAIL. It's called Swift Alignment of Image and Language, and this is also very recent, CVPR 2025. It's just presented in June, last June. And this is a very interesting paper because it tries to use pre-trained unimodal models for VLM training. So what does it mean? Pre-trained unimodal model. Modality is referring to either image, vision, or language, or audio, or text, right? This is called modality. Unimodal means the model is only understanding one modality. So Dino is a unimodal model because it only can understand images. But CLIP is a multimodal model because it can understand text and images. So in this paper, they take a unimodal vision model and a unimodal language model, and these are pre-trained on their respective own data sets. And they try to create a VLM out of these two independent models. So this is a very different approach. In CLIP, in SigLIP, you take an image encoder, a text encoder, and these are usually transformers, and you simultaneously jointly train them from scratch at the same time on a giant data set. But here, you take a pre-trained vision model and the pre-trained language model, and you try to align them to obtain a VLM. That's the different idea. So they first measure the alignment between pre-trained vision and pre-trained language models. And what they do is they take the vision model. This could be Dino V2, Dino V3, or something trained with SimCLR. So purely vision model, purely language model, and these are used as frozen. You put two linear layers on top of each other, and then use your contrastive learning loss, InfoNCE or sigmoid loss. And you train these linear layers on a captioning dataset, image caption dataset. They use CC3M. And they showed that image and language models, which are independently trained, so unimodal vision model, unimodal language model, they align pretty well. What does alignment mean? Let's look at the plot on the left. So x-axis is the ImageNet KNN classification accuracy. So this is like the success in unimodal vision task. Y-axis is the retrieval on an image caption data set. So this is a multimodal task. Both image and captions are involved. And you see a linear trend between the vision task and the multimodal task. This is what they mean by alignment. When you do the same thing for, in the x-axis, you have a purely language score. You get, again, a linear trend. The circles, the disk, size of the disk shows the parameter count. It's not performance. So they first show that independently trained vision models and independently trained language models are actually aligned, meaning that a better performing vision model is performing better when included in the alignment using this way, this alignment. This is a very important observation, because if we can do this, if this is working, then we can create a VLM by using this method. I take a pre-trained vision model, pre-trained language model, freeze them, and just train a shallow alignment layer on top of each other, and you get a VLM. You get something better than CLIP. And this is what they do. They take a vision model, a language model, they use them as frozen. They first extract the embeddings of images and text using an image text dataset like Lion. They actually use CC3M. And then take these embeddings, so these are the same, so these embeddings are the same, pass them through the alignment layer and use a contrastive learning. They actually use the SigLIP loss, sigmoid loss, and they only train this shallow 2 layers. Here is the loss that they used. XI, image embedding, YI, caption embedding, normalized. So this is classical SigLIP loss, okay? So this is nothing different, nothing new. And then, okay, for all experiments, they use Dino V2 large as the vision model, GTE and large V1.5 as the language model. So this flexibility brought by SAVE is very important because now you can use the strongest possible vision model and one of the strong language models, and you can combine the strength of these two things. And results are good. It's better than the striking result here is only using, let's see, so this 23 million merged means they merged CC12M and some other caption data set, and they obtained a 23 million image caption data set, 23 million pairs. CLIP was trained on, this version of CLIP was trained on Lion 400 million. It achieves 72.7% on ImageNet. SAIL achieves 73% on ImageNet. So using only 6% of image text data that CLIP uses, they outperform CLIP using only 6% of the training data. So this shows a true data efficiency in terms of image caption data sets. But of course, that unimodal models, so Dino, was trained on its own large data set, but no labels. And the language model was also trained on its own data set. But yes, it's a very striking result. And this paper proposes a new recipe for training VLMs. You don't need to train them from scratch using 500 GPUs, but you can take pre-trained strong models and only train shallow layers, and the training of this will be very cheap. You can train this at home. It's affordable. Okay. There are other VLMs. For example, contrastive captioners. So let's talk about this and then we'll take a break or, okay. I think let's take a break now, 10 minutes, and then we'll finish the remaining topics. Let's meet at 11:45. Okay. So other VLMs. So first of all, there are too many VLMs out there. Okay. There are too many VLMs out there, and I am deliberately not teaching many of them because it will just overload you for not a good purpose. It will just be noise. The essential ones are really a few, and I believe we went over them. But yes, just know that there are many other VLMs. For example, COCA, contrastive captioners. What they do is they do the classical contrastive loss between image and captions. They also add a captioning loss. So they add a multimodal text decoder which generates the caption. So this is the novelty that they did. So instead of just clip style VLM, you add a captioning task, and this makes your VLM better because there is now an additional task to train. BLIP also similar. They add a captioning task. They also had an image text matching branch. But really, these are the fundamental idea is still the same. One recent VLM, which is perception encoder, it was proposed this year, I think April 2025. And these perception encoder, these guys are adding videos, for example. Okay, so image, video, and you have large-scale contrastive pre-training. And among all the VLMs, I think perception encoder is now giving the best results on many data sets. They also have released a video dataset, video caption dataset. But yeah, as I said, there are many VLMs, and it's not really. We have seen the major ideas. Okay, now let's talk about. This is a very active area of research. There are many more. Now let's talk about this zero-shot, in quotes, zero-shot generalization. I have a question for you. Do you think a VLM trained on 400 million image caption pairs or 5 billion image caption pairs generalize to objects that it has not seen? I don't know, some kind of, let's think about an object, a weird object. Half of it is like an airplane, the other half is like a car. I don't know, some weird combination. Would it generalize to such a case, or would it generalize to different weather conditions? What do you think about the zero-shot generalization? No thoughts? It's not a trivial question. So to study this, researchers are working to study this, and there is this NeurIPS 2024 paper with the title, No Zero-Shot Without Exponential Data, Pre-training Concept Frequency Determines Multimodal Model Performance. So first, to answer this question, they need to identify the concepts and their frequencies in the image caption datasets. So you have this Lion 5 billion image caption dataset. There are 5 billion image caption pairs. But those captions are, as I have shown you, they are like free text. Some of them has hashtags, some of them has, I don't know, weird words. So you don't have clean concept or class names there. So the first thing is you need to identify concepts, and then you need to count them in that data set to see the frequency of how many that certain specific concept appears in the pre-training data set. So these researchers in this paper, they first get a list of concepts from the target data sets. So what is a target data set? These are the image classification data sets that you use to test your VLMs. So there is this, for example, satellite imagery data set, an image classification data set. But you take your VLM, CLIP, for example, and you take the vision encoder and fine-tune it on this satellite, or you just do the zero-shot recognition on this satellite imagery. And in this paper, they are interested in the zero-shot part. So the target concepts are important, okay? They take the list of concepts from the 27 target data sets. And this is basically concatenating all class names and making them unique. And at the end, 4,029 concepts, they call it concepts. they arrive at 4,000 concepts from 27 evaluation datasets. In ImageNet, for example, there are 1,000 classes. So 1,000 concept is coming from ImageNet. Other 3,000 are coming from the other 26 datasets. Now the task is to count the frequency of each concept within the image caption dataset, that massive 5 billion image caption pair. So first thing they do is there's a text index, so they count concepts only based on text. But this is also not trivial. You need to take care of the synonyms, acronyms, and so on. They also count them using the vision-based content. There's a image annotation model called RAM++. It takes an image and produces the concepts that image has. So at the end, they have 4,000 target concepts, and they count how many times, how many image caption pairs has that concept. Is it clear? So at the end, they have this concepts and frequency table plot. So there are 4K concepts. These are corresponding to distinct classes on 27 datasets. And frequency corresponds to how many times that specific concept is appearing in the pre-training dataset of the VLM. Obviously, some concepts appear a lot, but many concepts, a large number of them, appear very rarely. So you have a long tail distribution as usual. Okay? So they get this specific frequencies for concepts, and then what they do is they find the relation between the concept frequency and zero-shot accuracy on those target data sets. And look at this plot. It's a log linear plot. The x-axis is in the 10 to the power 1, 10 to the power 2. So this part is in the log scale, but this part is in part y-axis is in the linear scale. So this plot shows us that there is no true zero-shot generalization. If you are getting a high percentage accuracy for a certain concept, such as, for example, 75, 80%, it is because that specific concept is very frequently encountered in the pre-training dataset. So the more you have examples, the better your accuracy. Okay. This is the first observation. The second is, this is very striking. In order to make a linear accuracy increase, let's say from 70 to 75%, you need to add exponentially more data. Because from here to here, you need to add like multiple folds of data to get a linear increase in accuracy. So this is a very pessimistic scaling trend. In order to get, ideally, for a perfect vision model, you want to uplift all these accuracies to 100%. But this trend shows that to do that, we need to add exponentially many data to add. And that is beyond, I think, this data set has already seen almost all the visual data on the web, and it is still showing this pessimistic trend. So we have lots of things to do as researchers. This scaling trend is not a good one. We are obviously missing something, and scaling will not solve it. It's very obvious from here. We need some new kind of representation. I think this is my personal opinion. A new kind of representation that takes into account the latent structure in the physical world. physical world is hierarchical. There are physical constraints like the gravity and the light coming from above. These things actually constrain the latent structure in the visual world, and our representations should capture those things, should be aware of those things in order to increase this data efficiency. Otherwise, what we see today is the correlation and interpolation in the extreme scales. That's it. We have a correlation. We have good models that do statistical association correlation, and we have good models for interpolation, and we are throwing scale at them. Large amounts of data, large amounts of learnable parameters, and we are expecting them to solve vision, and it doesn't work, as you can see here. Okay, so this is the last slide. If you have any questions or comments, we can discuss. Yes, please.
The language scale is not that different.
Yes, it's different. In language, scaling trends are okay. And actually, if you increase the amount of data, if you increase the amount of learnable parameters, the accuracy is increasing linearly. Because language is synthetic, I think. And tokens are available from the start. But in vision, it's very different.